slideshow. Okay, today, we start the chapter 2, linear system of equations. It has two sections. Okay, definition of linear system of equation and properties, and Gaussian elimination and Gauss-Jordan elimination. Okay, in linear algebra, a solution of linear system is obtained by Gaussian elimination or with the determinant. In this chapter, we consider geometric meaning of the solution of a linear system and this solution, and investigate some applications of a linear system of equations. Okay. This is the definition of linear equations. Yeah, like this. If the linear equation with unknown xi's is of the following forms, with the real numbers ai's and b like this, then we call this is a linear system of linear equation. And if we have a set of linear equations, then it is called the linear system of equations. And these ai's are called as a coefficient, and these xi's are called the variables. And b is called the constant. Okay. Here's an example. A system of linear equations can be solved. And you have learned how to solve this by the elimination method, but not Gaussian elimination. But the method that you try to solve this problem was called the elimination method. You eliminate the variables from from the other, and so simplify it to get one value for one variable, and then use that to get the second value for the second variables like this. Okay? And this is an example of the linear and nonlinear equations. And this is not the typical form of the example for nonlinear equations. And these are linear equations, but this has 1/2 power instead of the degree. The degree is not 1 here. And this is not just the variables. So these are not the linear equations, but these are the linear equations. Okay, this is a set of linear equations, which is called the system of linear equations in general, and this can be written as this, as a linear combination of these vectors, like this. This linear system of equation can be written in a vector form, like this, as a linear combination of these vectors. Summation of xi, ai's is equal to the vector b. Okay? Okay. This is the easier way. Okay. In the system of linear equations, we can have three cases. One is the system has infinite many solutions, and the other case is it has single unique solutions, and we call for those cases, the system is consistent. And the case that the system has no solutions like this. If they are parallel, then they never meet, there are no solutions. Okay? So three cases. Unique solution, infinite many solution, no solution. That's the only three cases for linear system of equations. Okay. Particularly if this vector b, the bi's are all 0, then this linear system of equation is called the homogeneous linear system of equations. Homogeneous. And in this case, always, if you put zeros for all xi's, then that satisfies all this set of linear equations. So the zero vector is always a solution for this homogeneous system of equations. Okay? We call it the trivial solution. It's zero vector. Okay. When we have this set of linear system of equations, then we can easily find the solution for this x and y's. In that case, we call this g as a free variables, and the others are leading variables. Okay, we will generalize this concept in a systematic way by using the matrix. Okay. This process, you use the elimination process to find the solutions before. Now you're going to run a Gaussian elimination process to solve this large size linear system of equation in an effective way. Okay, the elimination method. Here, this is the system of equation in a vector form like this. And here, if we form a matrix with these vectors, AIs, like this, the first column here, second here, and the last here, then we can form a set of array of numbers, like this m by n set of entries, an array of entries. We call, let it be A, capital A, and define it as a matrix. Then we call these columns are called as a column vector, and we can call these rows as row vectors. Okay? Yeah, we learned about vectors in the chapter 1, and these main diagonal entries are called these main diagonal entries are called the main diagonal entries. Okay, here the ith row vector is can be written as this, and jth column vector can be written as jth 2d j's like this, in the parentheses. Okay. This is a notation for row vector and column vector from this A. Okay, with this notation, this linear system of equation can be written in this form: Ax is equal to B, where A is a matrix A, and B is a vector, and X is a vector like this. Then with this, if we multiply this and X, this A and X, then you will see this is equal to B. This is the exact way that we introduced. So this linear system of equation was written in the matrix form now. Ax is equal to B. Okay? And the solving linear system of equation has been studied from more than 2,000 years. So we can find the record from the Gujang Sansul, 9 chapters on the mathematical art, which was published in AD 263. So it's much more than 2,200 years ago. So this method was known long before the Gauss found defined it as his own method. Okay. Anyway, from this linear system equation, we can draw the augmented matrix like this. From Ax is equal to V, we can form a matrix A with this vector B here. So we can have m by n plus 1 matrix, augmented matrix. We call it this augment matrix. Okay. With this, we can deal with the earlier. You can deal with how to find the solutions of the linear system of equation. Before we start, we show some examples. In R3, if we have 3 equations like this, then each equation make a plane. So in this case, the 3 planes meet at one point here. So actually, this system of linear equation has a unique solution. Okay. For these other cases here, we have 3 equations, but as like you see, and these are actually a same equation, even though we have a 3 set of equations, linear equations, but these 3 equations are eventually same because it's just scalar multiple of it. So each planes are eventually same plane. So these 3 planes are parallel and overlap. So in this case, every point on these planes satisfies 3 equations. So we have infinite many solutions. In here, 2 equations are same equation, same plane, represent the same plane. So it has also infinite many solutions on this line. And here, these 3 equations can be drawn in R3 like this. As you see, there is this one line that satisfies all 3 equations, which is on all 3 planes. Okay. In this case, we have infinite many solutions. And the other case, the other third case, which is called inconsistent, it has no solutions, can be found in this way. In these cases, this example shows if these planes are parallel and does not meet any point, then actually what this means is there is no point that satisfies these equations, so third equations, isn't it? And this also, what this means is there is no point which on the all three planes. All this case, 1, 2, 3, 4. All this case, these are the case that these three equations, there is no point, no vector that satisfies these equations. That's on the all three planes at the same time. Okay. So these are the examples of inconsistent linear system of equation which has no solutions. Okay, now suppose we have this linear system of equations, then we can easily simplify this in this form. Okay, as you see here, we have 5 variables and three equations. Okay, and we have 3 leading variables, x1 and x3 and x4 only. So we have 2 free variables, which is x2 and x5. So let it be S and T, then all x1, x3, x4 can be written as a linear combination of this S and T, as you see here. So now we have a set of solutions that satisfies this linear system of equation with 2 variables. Okay? So this is the way that you have found the set of solutions in the earlier years. Okay? And this is the way that you write the solution, general solution. And this general solution can be written as a solution set like this, with 2 free variables. Okay? That's the way that you have learned. I will introduce you a new method, a new way of solving, finding the solution set. Before we start, we define a matrix. An array consisting of real or complex numbers is called a matrix, and each number is called an entry. This is called, the number of arrays like this is called a matrix. And the entries, each of Aij is called the entry. And this row vector is called the ith row of the matrix A, and this jth column is called the jth column of the matrix A. Okay? ith row of this is called the row of a matrix A, and the column, jth column here, is called the jth column of the matrix A. Okay. If we have m by n, n times n entries in here, then we call the size of this matrix is m by n. Okay, and if m is equal to n, then we call this matrix is a square matrix of order n. And this a's of I denote the ith row of A, and A to the j is denoted the jth column of A, the jth column of A. I have to fix it. 그러니까 여기 오타 있죠? 요거 이자 뺀다고 어디 표시해뒀다가 알려줘요. 고치게. Okay, so the matrix A can be written as the set of row vectors or set of column vectors like this, in the easier way. And this Aij over matrix A is called the ijth entry of the matrix A. And all Aii's are called the main diagonal entries of the matrix A. Okay. And this matrix can be written in this way. A is equal to the set of Aij's, of m by n matrix. Okay, or simply like this. Yeah, these are the example of the matrix. This is the example of 1 by 1 matrix, and this is the example of 1 by 3 matrix, and this is the example of 3 by 1 matrix. Coefficient matrix and augmented matrix of a linear system. Suppose we have this linear system of equation. This can be written as Ax equal B, where A, X, and B is like this. Okay? Then we call this A is called the coefficient matrix of this equation, and this matrix, m by n plus 1 matrix, is called the augmented matrix of the equation. Okay? Augmented matrix, 첨가행렬. Okay. Find the augmented matrix of the following linear system of equation. Then this matrix can be written as Ax equal B, where Ax, B are like this. So augmented matrix augmented matrix should be like this. Okay. This linear system of equation can be written in a matrix form like this. So augmented matrix is this plus this vector at the end, like this, as the last column. This is augmented matrix. Okay? Suppose you have a matrix like this, define the same matrix and the vector B, then you can generate the augmented matrix like this with this command. I will show it later at the end, all together. Next, Gaussian elimination. This is a new thing. This is the first new things for you in this chapter. Okay, augmented matrix. Okay. Like Gaussian elimination, which was appeared in 구장 산술 long ago, and Karl Gauss published a paper using this Gaussian elimination in 1809 in the theory of motion of heavenly bodies. 이제 천체 관측하면서 해성이 들어가는 궤도를 측정하기 위해서 많은 연립방 정식이 필요했는데 그걸 풀면서 그걸 손으로 풀기가 힘드니까 이런 방법을 찾아서 한 게 Gaussian elimination이에요. So he used this method to find the 해성의 궤도. Okay, now the following operations do not change the solution set. Okay, if you change the laws, when in the linear system equation, when you change the laws, there's no change in the solution set. If you multiply once a scalar on one equation, does not change anything on the solution set. If you multiply a scalar to one row and then add it to the other row, it does not change anything on the solution set. That's the way that you did the elimination. Okay? So we give the name. We call, particularly for third, this is called first and second and third elementary row operations for the matrix. And particularly type 3 elementary row operation is a row addition like this. Multiply k on the ith row and add the jth row of the matrix and put it in the jth row of the matrix. This is very important. Okay. In the following procedure. So actually this is the way that you have done your elimination, isn't it? And this is the same thing that you did on the matrix. Here, what you did, multiply -2 on the first row, first equation, and then add it to the second. And this is what you multiplied -3 on the first equation and add it to the third equations. Just to do the same thing on here. Multiply -2 and add it to the second row. That makes it 0. Multiply -3 on the first row and add it to the third row, which then makes it 0 like this. The same thing. This linear system equation is presented as a matrix form like this. Multiply 1/2 on the first row and then add it to the second row, which makes it like this. And multiply -3 on the second row and add it to the third row to make this 0. Like same thing. Multiply the -3 here and to add it to the third equation to make this term eliminated. Okay? Same thing. So now you have this linear system of equation and the matrix form like this. Here, you know what's the value of G, isn't it? Then plug it in here, then you get the value of Y. Plug in those values, Y and G here, then you have the value X here. This same thing can be done in here, isn't it? Here. So from here, G is equal to 3. So plug into G, you have Y is equal to this, and X should be this, like this. So from here, G is equal to 3, and plug in here to get Y value, and plug in Y and G value here to get A. So if you have this, you can rewrite it in this way to have this solution, easily. In this case, you don't have to use X, Y, and G, or here, and it saves your time and the papers, and also you can use other tools to do this simple arithmetic and algorithm, isn't it? That's the way. Okay. So from here we have found that X is equal to 1, Y is equal to 2, G is equal to 3. You have done it before like this. Now you learned the new way, which is called the Gaussian elimination. Okay. In order to do, we define a low echelon form and low reduced echelon form like this. Low echelon form, should satisfy n by n matrix E is called a low echelon form, then it should satisfy these three properties. First, there's no a row consisting of only zeros. It is placed on the bottom position. Every row which is consists of 0 rows should be on the bottom. Okay. Second, the first non-zero entry appearing on each row should be 1. Okay. The first non-zero entry at each row should be 1, like this. Okay, we call these leading entries. Leading entries are all 1. Third, if there is a leading entry in both i's row and the I plus 1's row, then the leading entry in the I plus 1's row is replaced on the right of the leading entry in the i's row. So it should be like a ladder, like this. Not 1 and 1 cannot be on this position. It should be shifted like this. So it should be like a ladder. Okay. So here this should be 1. Okay. So this is not in the REF form because this leading entry is not 1. Okay. But this is. Okay, and this cannot be happen because non-zero entry should be on like a ladder form like this. So this is not in the REF. Next, if it satisfies one more condition, the first condition, then it is called RREF, reduced low echelon form, reduced. Okay, if a column contains the leading entry of some row, then all the other entries of that column are 0. Which means like this. So among this, here like this. The above the leading one, everything's are 0. Above the one, everything's are 0. Then we call this form is called the reduced low echelon form. This can be done in the system of equation by when you can eliminate the other terms by multiply constant to delete this. In the system of equations. That's the same. That's the actually meaning. Okay, anyway, now we know REF and RREF. Okay, here. This is an example of REF. REF. Okay, REF. Here. This is REF. This is an example of REF. These are matrices in REF form. Okay, here. This is not RREF. The REF because the leading entry is not 1 here. And here, the 0 row should be on the bottom, but it's not in the middle. So this is not REF. And the bottom of leading one should be all 0, but this is not 0. So this is not in REF. Okay? This is an example which is not REF. And these are the example of RREF. Okay? There's the leading ones here, and above of the leading ones are all zeros. It's in the REF, and above of the leading ones are all zeros. Okay? These are the examples of REF. Leading one above 0, leading one above 0. These are okay. This can be any values. And all the 0 rows are on the bottom. Okay. So, the difference between REF and RREF is, if you have a non-zero entries in here, then it is just REF. But if you have everything above the leading ones are zeros, then this is in the REF, reduced REF. Okay, like this. Okay, the elementary row operation. So for the matrix, exchange i's row and j's row away like this. Or second type elementary row operation, just multiply constant, okay, on the one row. Or add the multiplication of i's row of a by k and 2 and add it to the j's row like this. Then this is third type elementary row operations. Important thing is these three operations does not affect the set of solutions when you applied it to the system of linear equations. Okay. If B is obtained from a matrix A by elementary row operation, then A and B are row equivalent. We call it they are row equivalent. Row equivalent. So from here, if we change the first row and second row to make this, and we divided, what we did? We multiplied, we changed, and from here we multiplied minus 3 here and added 2 here, which make this one. So these are row equivalent. And here, we divide by minus 2 on the second row to have this from C. So these are all equivalent. So these and these are all equivalent. And we multiplied minus 2 on the second node, add it to the first row to make this 0. So this gap from here. So all of these are row equivalent. Okay? Suppose finding REF and RREF. Suppose we have this matrix and find the REF and RREF by applying elementary row operations. Then, since 0 is here, so we replace it, replace the rows, and then multiply minus 2 to make this 0. And then this is done. This first column is done. Then consider second. And here, let's make this one 1 and make this one 0, like this and like this, by doing the elementary row operation. And then we have this. So we just multiply 2 on the third row to make this one 1. Then we have what? We have a REF, like this. Leading ones, we have 3 leading ones, and we have all 3 leading ones are 1s here. So this is in REF. Okay? And this is REF. Okay, what you have. From here, in order to have RREF, we just multiply 5 on the second row to add it to the first row to make this 0. And multiply 7 over 2 on the third row to add it to the second row to make this 0. And do something on here to make this 0 like this. Okay? So then we have what? We have REF and the above of the leading ones are all 0, so this is RREF. This is a simple algorithm only using 3 operations. Okay? If we have, we can find RREF by hand like this, and also we can use a code to find the RREF like this. Let's just simply show what we did. Here, the augmented matrix from this linear system of equation, 1, 1, 2, 2, 4, minus 3, and 3, 6, minus 5 like this, and B is 9, 1, 0, then augmented matrix can be found in this way, isn't it? And Gaussian elimination can be done in this way. And suppose we have this, then RREF can be found in this way. Is it same? Suppose we have a different matrix like this. Then also RREF can be found in this way. This algorithm, we can do the same thing by hand and by the computer as well. And as you see, this computation, this algorithm has been developed long ago, and even 1890. Yes. So, but as the computer has been developed, it's been stored, so we can do the same thing. Actually, yeah, if you go into this address, then you will see the calculator, matrix calculator that I have developed. So take a look and add your feeling on those machines. If you find any question, then ask it to me in Q&A, and I will answer it. It has all the code in it, so you can go through it when you need it. But now you don't need to bother, just go through how to find the REF and RREF to solve the linear system equation. That's more important. Okay, theorem 2.21. Two linear systems whose augmented matrices are row equivalent are equivalent. That means they have the same set of solutions. If the matrices, if the augmented matrices are equivalent, then they both have the same solution set. So this gives the whole idea. If you have a complicated linear system of equation and simplify it with the REF or RREF, and which is equivalent, and find the solution easily to find the original solution set. Okay? Actually, that's what you have done before. The Gaussian elimination is a method to transform the augmented matrix of linear system into REF and then solve. Gauss-Jordan elimination is the method to transform the augmented matrix of a linear system equation, REF, and find the solution set of the given one. Okay? And Jordan went one step further to from the Gaussian elimination. That's the only reason that Jordan name is there. Solve the following by Gaussian elimination. Suppose you have a linear system, then form an augmented matrix, then find the REF like this. Then, as you see here, G is equal to 3, and plug in here, then you will have a Y value, and the A value will be followed, like what you already saw, isn't it? This is an example that I showed in the first, isn't it? Okay? This from here, G, and Y is -1, and X is equal to 3, like this. Okay? So this can be done only by just finding REF of the augmented matrix. Okay? Solve the following system using the Gauss-Jordan elimination. From here, then you can find the RREF like this. Then you have the 3 leading variables and 2 free variables, and then you have what? Then you have put the free variables, let 3 free variables as R, S, and T. Then all the X1 and X3 and X6 can be written as a linear combination of those free variables R, S, and T. So you can find the whole set of equations, a set of solutions. Okay, with those, then you can write the set of solution as a linear combination of these 3 vectors like this, and the constant vector like this. Okay. Okay, so you have to learn how to find the set of solutions in this form for the large size linear system of equation, which you haven't done it before. Okay, you will have 20 equations with 25 variables, and you should be able to solve it. Okay, 그러니까 지금 알파고 같은 경우에는 이런 사이즈가 예를 들어 쉽게 얘기해도 400x400 매트릭스를 연립방정식으로 풀어서 그 답을 찾아가는 그런 셈이에요. 그거에 사실은 훨씬 더 400배 파워가 있는 그런 셈이지. 무슨 말인지 19x19에 20, 그 사이즈는 거의 그 빅데이터가 다루는 밀리언, 트라이밀리언 같은 그런, 트릴리언 같은 그런 사이즈의 매트릭스를 풀어야 되는 거예요. 그러니까 손으로 할 수 있는 문제가 아니에요. 무슨 말인지 알겠죠? 그러려면 이런 알고리즘을 이해해야만 하는 거예요. Okay, Gaussian elimination and Gauss-Jordan elimination has this much of difference to solve the linear system of equations. Yeah, we call in the REF form. These are called the leading variables, and these are called the free variables. Okay. And homogeneous linear system and trivial solution, yes, we have learned this. And if it's a homogeneous system, then augmented matrix is always looks like this, like the last column vector is 0. And say do the same thing to find the RREF or REF to find the solutions. Then as you see here, you will see leading variables are x1 and x3 and x6, and x2 and x4 and x5 are free variables. So x2, x4, x5 can be written as a free variables, LST. Then all the set can be written as a linear system equation like this. Isn't it? For the homogeneous system, you can find all the solution with just a linear combination of these three the free variables. Okay? But it's a non-homogeneous system, then you might have the other value, constant vector, with it. But homogeneous system, always this happens. Just a linear combination of free variables. Theorem 2.2.2, number of free variables in a homogeneous linear system. Okay, with n unknowns. If the RREF of the augmented matrix has k leading ones, then solution set has n minus k free variables. Like what you saw. You had a 3 by 6 matrix, and you had the 3 leading variables. So you had the 3 free variables. So addition of these 3 leading variables and free, like you have 3 leading variables and 3 free variables. All together makes the number of column of the vectors. Okay, 6. That's the idea. I will give you, we will have a rigorous proof on this in chapter 7 when we study the rank nullity theorem. Okay. And also another system of this always has a non-trivial solution if m is less than n. This is a homogeneous linear system of equation. It always has a it always has a solution already and the free variable. Since this is a homogeneous system, so if xi's are all 0, it's a trivial solution is always a solution. So there is a one unique solution already. And you have a free variables. So you have infinite many solutions when m is less than n. Okay. Homogeneous system with the number of equation is less than number of variables. Then it always has infinite many solutions. Okay. I think that's all. Okay, so I will summarize what you have learned. When we have the RREF of the equation, then this is called the leading variables, and these are free variables. So in addition of this leading variable and the free variable is actually the number of columns, isn't it? Number of columns, 6 here. So in this case, 1, 2, 3, 4, 5, 6 here. We have 6 columns. We have 3 leading variables, and the remaining 3 ones are free variables. So addition of 3 plus 3 is going to be 6, which is the number of columns. Actually, that's the rank nullity theorem. Okay. Now we are here, and I can review the chapter that we have covered here. Linear system of equation. We have seen the example 1, which is distinct what is a linear equation and what is not a linear equation. And this is example that has a unique solution, and these are the 3 examples that has infinite many solutions in R3, and these 4 examples are the cases which has no solutions in R3 when you have the 3 equations. And this is an example of the matrix of different sizes. And one important thing is the scalar can be written as a 1-by-1 matrix. And vectors also can be considered as a n-by-1 matrix or 1-by-n matrix. These are all matrices. So what you have learned so far are all a special case of a matrix now. And from a given linear system of equation, you can easily find the augment matrix. And with this code, you can find the solution for any other different problems or different size matrices to find the augmented matrix. And you can solve any type of linear system of equation by finding the REF and RREF. And you can solve the linear system of equation by finding this. For example, if you have this set of equations, then you can find the RREF here. So from this RREF, you can find the corresponding equivalent linear system of equation, which solution that comes directly from them, isn't it? If you have this form, you don't need to spend any time. Just this is a backward substitution. Just plug in the earlier value to get the whole solutions, to have the whole solution sets like this. If you have this type of homogeneous linear system of equation like this, then if you find the RREF like this, then you know it has an infinite many solutions, which can be represented as a linear combination of the free variables. I think that's it. And Gaussian elimination, you can find the augmented matrix and RREF, so you can easily find the solution set. X is equal to 2, Y is equal to -1, G is equal to 3, like this. You can use this code, which I made it more visibly for you. And you can generate the large size matrix like this. For example, if we have what? If we have 9, then how many? We can have 9 by 9 matrix. Then we have 9, 81. From 0 to 9, 0 to 8, you can have 9 by 9 matrix with this. You can generate random matrix to do the things. And actually, I have developed and also got a patent for such things that I just mentioned. Yeah, there are many ways to deal with this. I think that's the end of today's lecture, and you can take a look on my lecture in Korean and English as well in detail, and also we will continue the chapter 3 next class. And I'm looking for the team that will prepare for solving the solutions in give a presentation for the solution for the chapter 3 and 4. Okay, I want volunteers. I think that's it. Any questions? Any questions for chapter 2 and 1?